Just think about what Celsius is. We know that 0 degrees Celsius is when water freezes, right? And 100 degrees Celsius is when water boils, right? Now, the only other thing I really want to put down here is that we have very good familiarity with Celsius because the 0 point is when water freezes, the 100 point is when water boils. Now, I need to also say that those temperature measurements are valid on Earth at atmospheric pressure, okay? Meaning sea level pressure. If you go up into the mountains, or if you go to a planet with a much thicker atmosphere that pushes down, on everything more and then more pressure, then water is going to boil at different temperatures, because what's happening when the water boils is that it's basically the molecular bonds between the bonds, but the molecular attraction between the water molecules. When you add enough energy to it, it can escape and float out of the pot. But when you have the air pressure pushing down, it has to overcome the air pressure to pop out. So it's really a heat that you're applying there that's allowing the motion to get fast enough to overcome the external air pressure outside of the pot. So if you go up into the mountains, there's not as much pressure and the water's going to boil a lot easier. It's going to boil at a lower temperature, right? If you go to a planet with a very thick atmosphere that's really pushing down, then you're going to have to add a lot more heat in order for the thing to boil. So the 100 degree and the 0 degree Celsius markings are for Earth, atmospheric pressure, and of course at sea level, because the pressure changes when you go up into the mountains. Or if you could dive down into some kind of cave system or something, it would be a higher pressure there as well. So we have some familiarity with this. But let's talk about the Kelvin temperature scale, 0 degrees Kelvin. Now, I already made a mistake right there. We don't usually say 0 degrees Kelvin. We don't put a degree marking there. It's just by convention. We put the degree marking for Celsius and Fahrenheit, but when we talk about Kelvin, we just don't put the little degree mark. So even though I said degrees Kelvin, really, you don't really say the word degree usually. And at 0 Kelvin, the way you would say it is 0 Kelvin, atomic, thermal, motion, stops. Now I'm going to put stops in quotation mark. So 0 Kelvin is the theoretical temperature where, the temperature of an object is really just a measurement of how much energy or how fast all the atoms are bouncing off each other and moving. When you cool water down and it begins to freeze, the atoms or the molecules of water are moving slower and slower and slower. If you cool it down even further, they move slower and slower and slower. And if you get down to the theoretical point of 0 Kelvin, which is very far below 0 in Celsius, then theoretically the water molecules don't move at all. They literally have zero vibration. And when I mean 0 Kelvin is theoretically zero motion. Nothing moves. It doesn't even twitch, doesn't even vibrate even a little bit. Now, the reason I put stops, thermal motion stops in quotation mark, is because 0 Kelvin is a theoretical temperature. We can't really ever get to 0 Kelvin for a couple reasons. I'll tell you these reasons now, kind of just talking about it, but really there's a lot of research going into trying to reach colder and colder temperatures, right? In the laboratory, even today. The way that we cool things off is we always have to basically take the heat away from the object with a colder object. So if I have a glass of water and I want to cool down the water, then what do? I put it into a freezer, which is colder than the water. And the heat flows from hot to cold. And so basically the thermal motion of the water slows down. But where is that energy going? It's going into the freezer. So you have to have some colder reservoir to take the heat away. I could also put ice in the water, and the ice is colder than the water, and so then the water temperature goes down. But if you're trying to reach 0 Kelvin, where there is no motion at all, how are you going to have a colder reservoir than 0 Kelvin to take the heat away? We always have to have something colder in order to pull the heat out, but if 0 is really no motion at all, how can you have something colder than that to take the heat away? So getting to 0 Kelvin is just like getting very, very close, but it never gets there. We can never get to 0 Kelvin because it's impossible to have something colder than 0 Kelvin to take the heat away to get to 0 Kelvin. That's reason number one. Reason number two is because when you start talking about thermal motion of atoms and molecules, you have to talk about quantum mechanics. We're going to talk a lot more about quantum mechanics later. But just know that quantum mechanics is its own field of study. There's quantum physics and quantum chemistry, and it's our best theory of understanding how matter behaves on a small scale. And it turns out, I mean, I could summarize 100 years of knowledge of quantum mechanics in a couple sentences. It's impossible for something to ever stop moving. And the reason it's impossible is because of something you may have heard of in everyday language called the Heisenberg uncertainty principle. That's impossible for something to really ever stop moving, because if it were to stop moving, I would know the location of the atom, and I would also know the speed of the atom, because if the thing stops moving, I would know it's exactly 0 meters per second, and I would know it's right here. And you cannot know the speed and the position of an atom or molecule at the same time. You can't. That is just a violation of nature. I know you're thinking, well, that doesn't make sense. I can measure the speed of whatever I want. But that's because you're talking about everyday objects like baseballs. But when you zoom in on the quantum level, things don't behave the way that they appear to large objects around us. The rules are, they're different really. And they manifest themselves more on a smaller scale. So you can't know, the object cannot stop because it cannot have 0 or known position and velocity of 0 at the same time. So there's 2 reasons why we can't get to 0 Kelvin. That's kind of an aside, but that is an interesting aside. But still, we can still have a temperature scale. We can still call it 0 Kelvin. We just know that we can't really get to 0 Kelvin. Now in the lab all the time, we can get to 4 Kelvin, 3 Kelvin, 2 Kelvin, no problem. We do that with rocket fuel, liquid hydrogen, liquid helium, liquid oxygen. We do that all the time. Getting down to a millionth of a Kelvin or a trillionth of a Kelvin, that's where the research is. And people get closer and closer every year. So if we needed to draw a picture of these temperature scales, then we would draw the Celsius scale, something like this. We would say, all right, we have, how do I want to do this? Let's do something like this. Let's draw a thermometer that goes something like this. Yes, it's a hokey looking thermometer. I agree with you. And higher temperature is this way and lower temperature is this way. And we're going to draw a Celsius thermometer. So somewhere up here is what we call 0 degrees Celsius, and somewhere over here is called 100 degrees Celsius. So here is where water is going to freeze or begin to melt if you're warming it up. And when you continue heating it up, it's going to get to 100 Celsius, it's going to start to boil. So that's the Celsius temperature scale. Notice that when you cool something down to 0, you can get it below 0, no problem, because it's just going to get colder and colder and colder and colder. Now, eventually, because we know temperature is just the motion of atoms, if you keep making it colder, theoretically, then the atoms stop. Now, we already just told you they really can't stop, but they're going to get closer and closer to stopping, so there is some limit to the coldest temperature you can get. And so what is that? We have a new temperature scale to really talk about that. So let me draw this thermometer again, right underneath, like this. This is going to be the Kelvin temperature scale. And the way down here is going to be 0 Kelvin. Notice we don't put any degree symbol there, and it should be a capital K so instead of a lowercase k, so I'll try to do it like that, 0 Kelvin. This is the temperature that if you were to cool this ice cube or whatever it is, colder and colder and colder, it would theoretically stop. All the motion of the atoms would cease. They wouldn't even vibrate anymore. They would just literally be still. All right? And so if this is 0 Kelvin and this is 0 Celsius, then right here, this marking is 273.15 Kelvin, and this marking right here is 373.15 Kelvin. Now there's a couple things I want to point out and compare these temperature scales, all right? Notice that when we have the Celsius temperature scale, we can have negative temperatures, negative 10 Celsius, negative 20 Celsius, no problem, because the 0 point is up here at the freezing point of water. But in the Kelvin scale, because the lowest temperature you can have is 0, there is no negative Kelvin. You can't have like negative 15 Kelvin. It doesn't exist. The coldest temperature possible in the universe is 0 Kelvin, and you can never get that cold. We just talked about that. So all of the temperature measurements in Kelvin are always positive. That's reason number 1 we use Kelvin in chemistry, because it's always positive numbers, and dealing with negative numbers is kind of a drag sometimes. The nice thing about the way the Kelvin scale is set up is, notice that there's 100 tick marks between 0 Celsius and 100 Celsius. How do you know? Because 100 minus 0 is 100. But notice if we take these numbers, 273.15 minus, 373.15 minus 273.15, even though there's a decimal, when we subtract, we still get 100 tick marks. So there's 100 tick marks. And there's 100 tick marks here. And because we know there's 100 degrees between freezing and boiling, in both scales, we know the size of the degrees are the same in Kelvin and Celsius. That's important. The size of the degrees. When you increment by 1 degree Celsius and you increment by 1 degree Kelvin, you're going up the same amount because it's the same number of degrees in Celsius and in Kelvin. It's different in Fahrenheit. Fahrenheit's a crazy temperature scale because not only is the 0 point of the freezing and the boiling of water kind of some weird numbers, but also the degree sizes for the Fahrenheit scale is smaller and different than these. So it's nice that there's 100 evenly spaced tick marks in both scales. The size of the ticks are exactly the same. All right, and also there's no negative temperatures in the Kelvin scale. That's another nice thing. So the next thing we need to be concerned about is how do we convert back and forth between these guys? You can see from the diagram here that the temperature in Kelvin is equal to whatever the temperature is in Celsius plus 273.15. There's your conversion factor, but it's different than regular conversion factors. You don't multiply or divide in order to convert temperatures. You just simply add a number. So notice that at 0 Celsius, if I put 0 in here for 0 Celsius and I add 273.15, then I get the correct answer in Kelvin. If I put 100 degrees Celsius in here and add it, then I get the same correct answer that I wrote down here on the temperature scale. So you can see that no matter what temperature in Celsius you are, you're always adding 273.15 to it. So the Kelvin temperature at the same absolute temperature is just a bigger number. So in your mind, I want you to start thinking about Celsius temperatures and Kelvin temperatures, and at the same thermal temperature, the same actual temperature in reality, the Kelvin number is just bigger. And the Kelvin number is bigger by this constant number, 273.15. So in your mind, I want you to start thinking about Kelvin numbers are going to look bigger than Celsius numbers. That's just something you have to kind of drill into your mind. So these are the temperature scales that we're going to use in chemistry and in almost all of physics. But because Fahrenheit has been around for so long, we still need to know how to use it because you're going to go to work one day, something's going to be in Fahrenheit, and some compressor and a pump or something is going to be in operating range of this to Fahrenheit to that Fahrenheit, and you're going to have to know what that means. So we have to talk about the Fahrenheit scale a little bit. All right. So when we go to the next page here, the next board here, I want to talk a little bit about the Fahrenheit scale. All right. The first thing I want you to remember or know is the Fahrenheit scale, the degree tick marks between the freezing point and the boiling point of water, the tick mark sizes in the Fahrenheit scale is smaller and very different than Celsius. And it leads to it being kind of kind of like not very nice to work with. Right. And the way you can understand this is because you know that in the Fahrenheit scale, 32 degrees Fahrenheit is when H2O freezes, right? And you also know that at 212 degrees Fahrenheit, water boils, right? And I'm going to show you how we get this in just a second, but there's a equation that can convert to Fahrenheit when you're given Celsius. Fahrenheit is going to be equal to the fraction 9/5 multiplied by however many degrees you are in Celsius, and then you have to add 32. I'm going to talk about how this works in just a second, or why it works the way why it is the way it is right here. But all you need to really know is if you know some temperature in Celsius, you put it into this equation, you multiply by 9, divide by 5, which is the same thing as multiplying by the fraction 9/5. Whatever you get as an answer, you have to add 32 degrees to it. Then you're going to get Fahrenheit. Now you can start to see why Fahrenheit is like not a great system. And the reason it's not a great system is because you have to multiply and add, and there's a weird 32 in there. It's all coming from nowhere. Whereas here, yes, you might say, well, this is a weird number, but this is a much more natural system because the 0 point of the system is when thermal motion stops. The freezing point and the boiling point of water is just the numbers that they end up being in this system. We ascribe 0 and 100 degrees Celsius to those numbers because we use water so much, but water, other than being on Earth, is not that important. These are just other numbers that correspond to that in that temperature scale. But the tick marks are the exact same size. There's 100 tick marks between these 2 points here, but there is not 100 tick marks between these 2 points here. Let me show you that right underneath there. If you take 212 and you subtract 32, what do you get? You get 180. So there's 180 degrees between the freezing point and the boiling point of water in the Fahrenheit scale. 180, that's just it's a weird division, okay? Now, if we go back to Celsius, so this is I guess I'll put Fahrenheit here, kind of like to show you this. Now in Celsius, right? In Celsius, we know that water boils at 100 degrees and it freezes at 0 degrees. So there's 100 degree marks between the freezing point and the boiling point of water. 100 is a nice number because it's a base 10 number system, and our entire number system is base 10. So you can see that there's 100 degrees exactly between the freezing point and the boiling point of water in Celsius. In Kelvin, when you subtract these numbers, you also get exactly 100 degrees, so they're the same size. But in Fahrenheit, you don't get 100 degrees, you get some crazy number, 180 degrees. That means that since freezing and boiling of water are in the same fixed location on the temperature scale, if there's 180 degree markings, that means the degree size in Fahrenheit has to be much smaller, because you have to fit 180 little tick marks in the same space between freezing and boiling of water. So the degree size is smaller. And because of that, it leads to an ugly looking equation that we have to learn how to use. Now let me just kind of show you real quick that what this is basically saying, there's 180 tick marks in the Fahrenheit scale compared to the 100 tick marks in the Celsius scale. So if you write a ratio here, if you make a ratio, which we know we can write ratios as fractions, right? We can make the ratio 180 compared to 100. This means the number of tick marks in the Fahrenheit scale compared with the number of tick marks in the Celsius scale, right? Then we can simplify this fraction by dividing by 2, dividing by 2. And what do we get? When we take 180 divided by 2, we get 90. And when we get 100 divided by 2, we get 50. But we realize that we can actually simplify this as well. We can divide by 10. We can divide by 10. And so what do we get here? We get 9/5. Now you can start to see where the 9/5 is coming from in the equation. The 9/5 is coming from the fact that there are 9 degree markings in the Fahrenheit scale for every 5 degree markings in the Celsius scale. And that is because there's 180 tick marks in the Fahrenheit scale compared to the 100 in Celsius. This fraction just reduces to 9/5. So the way you set this thing up is, you say, all right, if I want to calculate Fahrenheit, then if I know that there's nine tick marks in Fahrenheit, so I'll write it like this, how did I write it here? I did this a second. 9 ticks in degrees Fahrenheit for every 5 ticks in degrees Celsius. If there's 9 ticks in degrees Fahrenheit for every 5 ticks in degrees Celsius, because the tick sizes are different, then what I'm going to do is use that as a conversion factor. And then I'm going to multiply by, if I'm trying to convert from Celsius to Fahrenheit, I'm going to multiply by the actual number of degrees Celsius I have. Notice these are going to cancel because it's on top and bottom, and you're going to be left with some degree Fahrenheit. But there's a problem. Because in the 0 points of these scales are different, because 0 Celsius is the freezing point of water, but actually 0 Fahrenheit is not the freezing point of water. 32 Fahrenheit is the freezing point of water. So not only do we have to adjust for the fact that the tick mark sizes are totally different in these scales in order to convert them, but once we get the amount of degrees in Fahrenheit by multiplying like this, by multiplying by 9 dividing by 5, that's going to get us into the Fahrenheit scale. But then we have to add 32 degrees to it because the freezing point of water is at 32 degrees. We have to shift it up, in other words. So we add 32. So the 9/5 times the Celsius is basically taking the number of degrees of Celsius you have in your problem and converting it to the number of degrees of Fahrenheit, because there's 9 times the degree tick marks in the Fahrenheit scale compared to the 5 in the Celsius scale. So this converts to Fahrenheit, but because the 0 point of freezing is different in both scales, we have to add 32 degrees to bring it up so that we shift the thing up, so that, because the two scales are shifted relative to one another. The 0 point in Fahrenheit, the freezing point of water is 32 compared to 0, so we have to shift the thing up. So the 9/5 is converting to the Fahrenheit scale. The plus 32 is shifting it so that they match with 0 degrees Celsius. Now you can check this, because if you want to convert 0 degrees Celsius to Fahrenheit, what do? You put 0 in here. 0 times any fraction is 0, and then you add 32, and you get 32 Fahrenheit is the same thing as 0 Celsius. So that makes sense. And if you do the same thing, if you take 100 for Celsius, and if you take 100 times this, 100 divided by 5 is 20, and then the 20 times the 9, you get an answer there. You add the 32, you're going to get 212. Go ahead and check that out for yourself. Now, the reason I'm going through so much length to talk about how this is created, what this formula means, is because in the next lesson, we're going to have a problem that's very similar. It's not going to be quite the same as this, but it's going to really require us to know how to do that. That's kind of why I'm doing it. So for now, what we want to do for the rest of this lesson is just get practice with these equations, which are very simple. To convert from Celsius to Kelvin, then you just add 273 to the Celsius and you get the Kelvin. To convert the Celsius to Fahrenheit, then you have to put it in here, multiply by 9, divide by 5, and then you add the 32 and you get the Fahrenheit. So let's do some problems to practice going back and forth between these three temperature scales. All right, so for problem 1, or part A, I guess you'd say, let's convert 72.0 degrees Fahrenheit to Fahrenheit, and let's go to degrees Celsius. Now, right out of the gate, this one's a little trickier, right? Because let's write down the equation. We know that degree Fahrenheit is going to equal to 9/5 times whatever the degree Celsius is, and we add 32. So normally you put stuff on this side and you calculate the Fahrenheit, but we're actually given this. So you have to use your math skills too. I mean, this is chemistry, along with physics, is a mathematical science. We expect you to know how to solve an equation. I'm going to help you if you don't really remember, but if you're uncomfortable with x's and y's and adding and subtracting on an equation, then you really need to go back and understand that material. It would be like going to France and you've never ever looked at a French-speaking, French-speaking class, taken a class, or you don't know anything about speaking the language. You just go there. You're not going to know anything. So what we do is we take the 72, we put it here, 72.0, because that's actually the Fahrenheit temperature we have. And on the right-hand side, we have 9/5 times C plus 32. How do you solve this equation? We need to solve for this. A lot of students, when we're in math class, they're like, why would I ever need to learn how to solve this equation? Here's a good example. I give you an equation to go from one direction to the other, but I immediately make you go the other way. And so a lot of students don't know what to do, but it's very simple. The first thing we need to do is get rid of the 32 over here. What we'll do is we'll subtract 32 from both sides. We'll have 72, and then we'll have minus 32, and that's going to give us 9/5 times C. Now, when we take 72 minus 32, we get 40. So we have 40 is equal to 9/5 times C. Now, how do we get C by itself? Well, just like we can add or subtract both sides of an equation, anything we want, we can also multiply or divide. We want to get rid of the 9/5. How do we do that? We multiply one side by 5/9. Whoops, if I can write 9 correctly. 5/9. And we multiply this side also by 5/9. And why are we doing it that way? Because the 5 on the bottom and the tops cancel, and the 9 on the bottom and the tops also cancel. So what you're going to be left with is 5 times 40 divided by 9. And when you take 5 times 40 and you divide by 9, you're going to get 22.2 is equal to C. And so we flip it around, you say C is equal to 22.2 degrees Celsius, because we're going into the Celsius scale. And that's the answer, 22.2 degrees Celsius. So if I had told you, hey, 22.2 degrees Celsius, convert it to Fahrenheit, you would take that number, you would stick it here, multiply by 9, divide by 5, then you would add 32, and you would get 72. We had to go backwards, though. We put this in place here, and then you have to use the rules of algebra. We want to solve for C, the amount of Celsius degrees that we have. So we first subtract 32 from both sides. That gives us 40. To get rid of the fraction, we flip it over and multiply. That cancels everything and gives us, when you take 5 times 40 and then divide it by 9, 22.2 degrees Celsius. All right, so once we've got the first one out of the way, the rest are going to be a lot easier to understand. So let's take a look at the second one here, which is, let's convert 216.70 degrees Celsius. Let's go to degrees Fahrenheit. Now, the equation is exactly the same equation. You start to remember it after a while. Fahrenheit is equal to 9/5 times Celsius plus 32. So we say Fahrenheit is equal to 9/5 times Celsius plus 32. So we just stick the Celsius right into this position. And Fahrenheit is 9/5. And then we have multiply by 216.70, and then we add the 32. All right, and what do we get over here? When we multiply, we take the 216.70, we multiply by 9, then divide by 5, or multiply by 9/5, exactly the same thing. You get 390.06. You still have to add that 32. And so the Fahrenheit, once you add those numbers together, you get 422.06 degrees Fahrenheit. And that's the answer in Fahrenheit. So straight plug in, multiply by 9, divide by 5, then you add the 32, and this is the answer. You get 422.06. All right, now we're cooking. Let's go to part C. Let's convert 233.0 degrees Celsius. Let's go into Kelvin. Notice I did not put a degree symbol there. I might accidentally mess up and do it sometimes, but technically you're not supposed to put a degree symbol next to the Kelvin. It's just 45 Kelvin, 36 Kelvin. You never say degrees Kelvin, right? So what is the equation to go from Kelvin to Celsius? You should, in your mind, think, okay, Kelvin and Celsius are related. Kelvin's always bigger. By how much? 273.15. It's bigger than Celsius. So this is the equation that we use. So the equation that we use is we say Kelvin is going to be equal to Celsius plus 273.15. And we're converting to Kelvin, so we just stick it right in there. This number goes right into here, 233.0 plus 273.15. And so what we get is 506.15, and then we're going to round because we have too many decimals here. So we're going to say that this is 506.2, and we don't put degrees Kelvin, we just put Kelvin. So Kelvin is 506.2. All right, let's take a look at the next problem, D. We have to work a little harder for this one. Let's take a look at the following, 315 Kelvin. Let's convert it into degrees Fahrenheit. Now, there is no equation to go directly from Kelvin to Fahrenheit, right? Because we have an equation that goes from Kelvin, or that relates Kelvin and Celsius, and we have another equation that relates Celsius and Fahrenheit. So, of course, you could play with it and come up with a single equation that would work, but I haven't given you one. So it's best to do it in 2 steps. Let's convert the Kelvin into Celsius, and then once we have the Celsius, we'll then convert that into the Fahrenheit. So, to go from Kelvin to Celsius, what do we use? We remember that Kelvin is bigger, so what we say is that the Kelvin temperature is going to equal to the Celsius temperature plus 273.15, like this. Now we know the Kelvin temperature, it's 315, and we're solving for Celsius. How do we solve for Celsius? Well, we're adding here, so we just need to subtract on both sides. 273.15, that gets rid of it here. 315 minus that gives you a Celsius temperature of 42 degrees Celsius. Of course, we're rounding here because we have a decimal here. Once we round it, we get to 42 degrees Celsius. Now, once we have Celsius, we go over to the second part of the problem. And we remember that the Fahrenheit temperature is just 9/5 times the Celsius temperature plus 32. And now we just stick the value of Celsius in here. And so what we get is 9/5, and this is multiplied by 42, and then we add 32 to it. All right? So when we take 42, multiply by 9, divide by 5, what we get is 75.6, and then we still have to add this 32 to it. So when you take 75.6 and you add the 32, you'll get 107.6, but that's, we want to round to the correct number of significant figures. So we have too many digits here for our answer. So what we have, then, I'm just going to round it to 110 degrees Fahrenheit. 110 degrees Fahrenheit. Now, I know we talk about significant figures and things like this. We're going to get into that a lot later. So right now, we're just going to talk about the idea of, you know, you don't want to carry too many decimals in your answer because you know that the accuracy of the numbers that you were given is fixed. So you don't want to carry like 1,000,000 decimals into your answer. It doesn't make any sense. So we just round it to 110 Fahrenheit. All right, so that was D. We only have 2 more of these guys. Let's crank through those in the next little board here, and we will be done. So we have the following. What about 2,500.0 degrees Fahrenheit? And let's convert that to Kelvin. Same thing, I don't have an equation that goes directly from Fahrenheit to Kelvin, so I'm going to break it into 2 parts. I'm going to go to Celsius first. I know that Fahrenheit is equal to 9/5 times the Celsius temperature plus 32. But I'm given the Fahrenheit temperature, so that has to go here, 2,500. I'm just going to drop the decimal. I know it's 2,500.0. 9/5 times Celsius plus 32. So the first thing is I have to subtract 32 from both sides. So whenever I subtract 2,500 minus 32, I'm going to get 2,468, and that's equal to 9/5 times Celsius. I just subtracted 32 from both sides. Now, how do I get rid of the 9/5? Well, I'm going to multiply both sides by 5/9. and I have to do it there, I have to multiply here also by 5/9. So I'm going to have a cancellation. The 9s will cancel and the 5s will cancel there. And then I'm going to flip it around and say, all right, Celsius temperature is going to be the, let me just catch up to myself here. The 2,468, I'm going to multiply by 5, I'm going to divide by 9, and when I do that, I'm going to get 1,371.1, and that's going to be degrees Celsius. So 1371.1 degrees Celsius. Okay, so now I have Celsius, and then I can go from Celsius to Kelvin. So what is the relationship there? Kelvin is bigger. How much bigger? It's the Celsius plus 273.15. And now I know this number. So the Kelvin temperature is going to be 1371.1 plus 273.15. And so the Kelvin number, 1371.1 plus 273.15, is 1644.3. And that's rounding, of course, and that's Kelvin. Now, you don't usually put a degree symbol there, so just kind of write it with a K. 1644.3 Kelvin. So a lot of students, when they get to this kind of problem, they don't know what to do because they're like, well, you didn't tell me how to go from Fahrenheit to Kelvin. Well, you got to go in steps sometimes. You got to use what you're given and kind of like chart a course through the math to get from point A to point B using what you know. And if you don't really know a single equation, then you have to do 2 steps sometimes. And you have to be careful because if you make a mistake in the first part, then it will ripple into the second part. And of course, you won't be a very happy person there at the end. All right, here's our last problem. 0 Kelvin. Let's convert that to Fahrenheit. All right, well, we can't go from Kelvin directly to Fahrenheit. So we just know that the Kelvin temperature is equal to the Celsius temperature plus 273.15. If it's 0 Kelvin, 0 goes here. Then we have Celsius plus 273.15. And then if you subtract this from both sides, it's 0 minus this, so it's going to be negative 273.15. That is the degree Celsius. So it's 0 Kelvin, it's equal to negative 273.15. Then we go to Fahrenheit. We say, all right, we know that Fahrenheit temperature is 9/5 times the Celsius temperature, and then we have to add the 32 degrees. But the Celsius temperature is a negative number. No problem. We can handle that. 9/5, then negative 273.15. That is the Celsius temperature, and we have to add that 32. So when you take negative 273.15 and then you multiply by 9 and divide by 5, you're going to get negative 491.67, and you have to add that 32. So this becomes negative 491.67, add the 32, and then you're going to get negative 459.67, and that's degrees Fahrenheit. So you can see it's just a weird number. It's just very, 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 very large negative number, negative 459.67. So in this lesson, we've covered a lot. We started off talking about Celsius, something that everybody has familiarity with. Freezing point, boiling point of water. 0 is freezing, 100 is boiling. And then we said, okay, when we're talking about chemistry and physics, we need a temperature scale that includes, or that's more natural. And it's more natural to talk about 0 in a temperature scale to be when all motion stops, because that is what temperature is. It's a measure of the motion. You call it thermal motion of the atoms or molecules in the substance, okay? So we say 0 Kelvin is that point, and that's going to be our temperature scale. All thermal motion stops. And then we say that leads to a nice couple of things. Number one, the temperature scale in Kelvin is always positive. There's never any negative temperature, so that's nice, number one. And because we set it up this way, then we have the same number of tick marks between freezing and boiling point of water, and so the tick sizes in these scales are the same. It's very easy to go back and forth. You just add, or maybe you have to subtract a number. But because the Fahrenheit scale has these crazy endpoints of freezing and boiling point of water, with 180 tick marks compared to the 100 tick marks, it leads to the ratio of 9 temperature tick marks in Fahrenheit for every 5 temperature tick marks in Celsius, because the tick marks are smaller in Fahrenheit, okay? And that leads to this crazy equation, 9/5 Celsius, and we have to add the 32 because the 0 points it's not 0 degrees at the same point, at the freezing point of water. It's 32 degrees versus 0, so we have to shift the numbers up to get to the same place. And then we solve the problems. You need to be comfortable with that because later in chemistry, chemical reactions, especially when it comes to gases, they're all going to be specified at a certain temperature. Reactions actually happen at different speeds, rates, and sometimes they don't happen at all unless they're at a certain temperature. you may have noticed that you can't really burn things very easily without giving some temperature, giving a match under here. The match adds some energy into here, and then the reaction can take place. So we're going to talk all about why that's necessary, but you can see how chemistry is very closely tied to temperature, because chemical reactions, even simple ones like burning, very much related to temperature. And so we're going to do a lot with that in the future. So this was part 1. I'd like you to follow me on to part 2. We're going to continue talking about chemistry and solve one more completely different type of problem to exercise our skill with temperature scales in chemistry. Learn anything at mathandscience.com.